Hello, my name is Fan Shimeng. I come from Frankfurt University. Today I will discuss the ultra-strong coupling of plasmonic metamaterial and photons in a terahertz photon crystal cavity. This is the content of my presentation. First, I give you a brief introduction on the background and motivation. Then I will discuss the main work is metamaterial cavity electrodynamics. And lastly, give you a summary. So cavity ED and cavity QED has been investigated over a long time. It investigates light matter interaction in a cavity environment. So in this cartoon, you see the gamma is the K rate of the material, and kappa represents the K rate of the cavity, and G represents interaction between material and photons in the cavity. If 2G is larger than average of gamma and kappa, the material system is in a strong coupling regime. So without a strong coupling, if the resonant frequency of the material and cavity is the same, and then in transmission spectrum, you only see one transmission peak. If there exists in a strong coupling regime, you will notice that in the transmission peak is split into two new peaks. It is called polariton modes. The frequency difference between these two polariton modes is called Rabi splitting. If you fix resonant frequency of the cavity of material and change another one, you will notice this typical anti-crossing feature. This kind of anti-crossing is typical of cavity QED. Cavity QED has been investigated with a lot of different materials. Like at the beginning, people invested with atoms, then invested with quantum atoms like quantum dot, quantum well. And also recently, there's investigation using molecules and also secondary resonance in 2D electron gases. And here we're interested in strong coupling with metamaterial. And this is a typical metamaterial. If you have a light polarized in this direction, you notice that your drive carriers oscillate and forms effective electric dipole. And our motivation is, does this effective electric dipole can also strong couples with photons in the cavity? So that comes to the experimental part. So the metamaterial we used is a Swiss cross metamaterial, and it has a resonant frequency of lines around 0.9 terahertz. The red line is simulation from CST, and the black line is measurement with the TGS measurement. The cavity we used is 1D photon recurrence cavity. It just to periodically arrange silicon air. In the middle one, you have the defect layer, which has slightly thicker. And the cavity we built had a resonant frequency around 0.87 terahertz. And the red line is measurement with the TGS. It has Q factor of 86. It's quite high. And here it shows the electric field distribution inside the cavity. And in order to achieve the strong coupling between electric dipole with electric field, then we need to put a metamaterial on the surface of this defect layer where you have maximum electric field. Again, here shows the resonant frequency of the metamaterial and resonant frequency cavity. If we put a metamaterial inside the cavity, then we notice that there's originally one peak split into two peaks. And the splitting between these two polariton modes is about 34% of resonant frequency cavity, which means we already achieved an ultra-strong coupling regime. So then we can also vary the resonant frequency metamaterial by changing the different sizes, and we can notice the change of the polariton modes. And then we can determine the low polariton modes and upper polariton modes with the eigenvalues. And the dashed line is simulated freestanding metamaterials. And we can understand this one with a coupled harmonic oscillator model. So just like coupled to pendulum. So we can derive their new eigenvalues from this coupled equation, and they can fit the experiment quite nicely. So from a theory of cavity QED, the Rabi splitting is proportional to to the effective dipole moment here, and also proportional to vacuum electric field of the cavity. So as we notice here in the cavity, in the center of the cavity, the electric field is almost zero. That means the vacuum electric field is zero. And then if we put a metamaterial in this position, you have a zero Rabi splitting. So to test that idea, we did the simulations, but put the metamaterial in different positions of the defect layer, and then we know indeed we find that in the simulation, the Rabi splitting increases if you move the metamaterial close to the surface. And the derived vacuum Rabi splitting is indeed shows linear dependence to a function of vacuum electric field. So we also can realize strong coupling between the spin-ring resonator with the cavity photons. And this is a typical anti-crossing feature, and also can simulate it with anti-crossing feature with a coupled harmonic oscillator model. And also we'll notice from here that the Rabi splitting is also proportionate to the square root of number of the unit cells in the beam. But to test this kind of feature, we can just change the density of the metamaterial by changing the size, the period. And we cannot use in Swiss cross metamaterial because they have a strong coupling between the neighboring unit cells. So we can use the spin-ring resonator, just change the period, but fix the size. Okay, then we do find that if we increase the density of the unit cell, and we find the Rabi splitting increases. And the Rabi splitting as function density can be fit nicely with the screw dependence, which means it is not the individual unit cell that interacts with photon, but it's a collective of ensemble of all the unit cells interact with photons. And we notice that also in this electric field distribution, we have on both surfaces of the defect layer, we have a maximum electric field. And then if we put 2 layers of metamaterial on both sides of the cavity, even though they are spatially separated, what do you expect? You do expect a stronger polariton amplitude, or you expect a stronger splitting. Yes, we did experiment. We find that by putting 2 layers metamaterial inside the cavity, the Rabi splitting increased by square root of 2. That means the 2 layers also interact collectively with the photon, even though they are separately in space. So, but now to give you a summary, we investigate the strong coupling of metamaterial as artificial photon with the cavity photons, and the coupling strength increasing linearly as a function of the standing wave electric field inside the cavity. And a strong coupling shows a non-local collective interaction feature. And such investigation can be used for sensing, for modulator, for switches, and also can be used to generate a polariton laser. And by now, I thank you for your attention, and I'm glad to take your questions.